Hello everyone. Thank you for joining us for today's webinar, Uniform Conditioning in Studio 3. Our presenter for today is Jono Graham. Jono is an experienced geologist who specialises in the fields of geostatistical resource modelling, resource estimation and risk analysis. An expert user of Studio 3, Jono has carried out numerous geological resource modelling consultancy projects for major mining companies across the globe, dealing with a range of commodities including gold, lead zinc, copper gold, nickel sulfide, coal, phosphate and aggregates. Take it away, Jono.
Okay, hi everybody. Hope you can all hear me. I'm going to share my screen. Just bear with me for a couple of seconds while I do this. Okay, so thanks everybody for joining us. Thanks for your time. I'm going to give you a run through on the new functionality in Studio 3, uniform conditioning. It's a new module available in release 24, which is actually out yesterday. So I'm going to run through a presentation. The main focus of this will be a presentation, and I'll give a brief demonstration at the end, just so you can see for yourself the new functionality. So the flow of the presentation, I'm just going to set the scene. What's the problem and what problem needs resolving, which is in fact the effect of smoothing, and going to talk about the smoothing effect on mining, the sort of the issues that come out of mining. And then talking a bit about uniform conditioning, then localized uniform conditioning, how the process works in Studio, and also just touch on some future developments as well. So the challenges that need to be addressed, that's reasons why we might want to look for a different method of estimation. Lack of sample data, estimating into large panels, and reporting global grade tonnages may not be appropriate at the mining scale. And this is prevalent in early stage projects where you're drilling on a large grid and also having large drilling patterns. You much got to have large blocks. So just a very informal summary of current practice. You carry out your geostatistical analysis on your validated data set. Use your panel size based on the sample spacing. Heuristically, that's roughly about half the drill hole spacing, something generally supported by KNA analysis. Estimate into your domains, and you determine the global grade tonnage curves, and then calculate the classification of resources based on geological continuity, sample spacing, etc. So that's a brief summary of what you do. So what's the catch? What's the problem with that approach? The global grade tonnage that we produce from that is representative of the entire model, and the domain averages are certainly representative of the domain. But smoothing is introduced, and this is a natural outcome of linear estimation. So the smoothing effect, well, why does this matter? Linear estimation naturally produces estimates, averages based on sample data sets. So on a local scale, we'll always find the greatest smooth. And even on a panel scale, we'll find the same. We don't produce any estimates which represent values matching or exceeding the highest value of the deposit. Never reproduce zero grade, always something in the middle. So what effect does this have on mining? The resource model that we produce certainly provides an accurate representation of the global mean grade and grade tonnage curve that could be expected on a global scale. But what it doesn't represent, crucially, is the regions within the panel at the SMU scale, so recoverable resources that could be mined selectively. If you look at this diagrammatic, we have got samples represented by the blue dot, and then we've got the large pastel shaded squares, which kind of represent the grades that have been estimated in blocks. Block is roughly half the space. So in terms of the drill hole spacing, the large panel is chosen is certainly the correct thing to do, but what it ignores is the SMU size. And if you can see in that sort of central panel, you can see that there's variability that naturally will exist within the panel, but it's been completely masked or smoothed through the linear estimation. And so we tend to lose sight of the recoverable reserves when we are just looking at the grade tonnage curve on the entire model. The SMU is obviously usually smaller than the panel sizes, so the grade tonnage curves and mine plans based on the resource model blocks usually not representative of what can actually be economically recovered. So if we just check out some examples, just a few graphs to show you the sort of tangible outcome of smoothing. So this is a quantile plot where we're plotting the quantiles of the samples on the x-axis against the estimates on the y-axis. And if you look at the x-axis of about 200, grade of 200, and you read up to the block grade, you'll see that you have slightly higher block grade, although it's at the low end spectrum. And the result, the reason for that is your higher grade samples be used in the estimate as well as the low grade samples, and so the block as a whole would be slightly higher grade than perhaps the samples in that the local samples within that region. And the same can be seen at the high spectrum. If we look at the grades of say 600 to 700 in the samples, the estimates we're tending to get sort of 400 to 500. So they have been, the blocks have been devalued by incorporating low-grade samples. So the sort of smoothing effect. And that this can be seen in this graph as well. So we've got the black line representing the samples, and the green line representing the block estimate. You can see that the curve abruptly reaches a high percentage frequency. The green line at relatively low grade compared to the samples represented by the black line, where we see we've got sort of quite a long tail of high grade. But those high grades have effectively been smoothed away into the larger block. So in the context of mine planning, the grade distributions appear differently if we compare the resource model to the SMU scale. And if we take a look at the grade tonnage curve associated with this, comparing the 80 by 80 SMU, which is the example in this case, a sort of smooth S shape, compare that with the tonnage grades sample level SMU. You can see, looking at the blue line, we've got potentially higher tonnages. We have got tonnages at higher cutoffs, where if you compare that to the green line, the grade drops off very quickly, or the amount of material drops off very quickly at high grade. So potentially, in terms of the recoverable resources, we're losing the information specifically, or more importantly, relating to the high-grade data, which is going to add value to our deposit. So uniform conditioning is an approach that you can take. It provides a method for creating models that is representative of this variability for a defined SMU. And you can then use this SMU model for mine planning and reserve calculation and increase confidence in the resulting report and mine plan. So just to go through a little bit about uniform conditioning analysis. So uniform conditioning itself is a non-linear geostatistical tool in contrast to methods such as inverse power of distance or ordinary or simple kriging, which are linear methods of estimation, and this is a non-linear approach. And it's used to determine the distribution of grades above specified cutoffs inside your block model panel, parent cell, or at an SMU level. And it's generally used to produce a model that represents the variability of grades at a defined SMU. So we generally carry out the analysis to give grade tonnage curves at a range of different SMU sizes, which is good because this allows the assessment of recoverable resources at different scales. For a study of uniform conditioning, firstly define the SMU that we were going to use at the deposit scale. Then the local distributions are estimated at the panel scale. And when we say panel, I guess we interchange that with the parent cell. So the larger, if aligned grid is parent cell, and the light grey, smaller grid would be the SMUs within the parent cell. The panel size is obviously chosen to ensure suitable kriging quality. And then the grade make panel the smooth approach, smooth outcome of grade. And the local estimates are then conditioned by kriging. So in each panel, we get a grade distribution, and then the preliminary localization condition model is performed on a panel-by-panel basis. So over and above uniform conditioning, we can also then take this to another level called localized uniform conditioning, which not only gives us the grade tonnage curve of different SMUs within a panel, but we can also assign grades at the SMU scale. You can see we've got more granularity in the cell. So localized uniform conditioning is actually a post-processing function carried out on the uniform condition model. The process analyzes the grade tonnage distribution for each panel to define the individual SMU grade. And the SMU grades maintain their spatial distribution, which is obtained by ordinary kriging. So in terms of the process of localized uniform conditioning, the SMUs are ranked by directly kriging the blocks using ordinary kriging. So they're given a first pass grade, and you get a distribution of grades at your SMUs. And the SMUs are then ranked from low to high grade based on their krig estimates. And then the ranked blocks, ignoring the ordinary krig grades, are then actually assigned grades based on the uniform condition grade and tonnage distribution is unique to each panel. Okay, so that's a bit of background about uniform conditioning and localized uniform conditioning. So now to touch on this process and how it's being implemented in Studio. So process is the first feature in Studio 3 following DataMine's collaboration with GeoVariant. DataMine has incorporated discrete processes that exist in GeoVariant's started to make an intuitive workflow-based process. Because we call it uniform conditioning and localized uniform conditioning, but of course there are processes that you need to run in the background as part of this study. So those sort of discrete processes have been put in place for workflow based with it. And in version 24, the new process can be found under Model Uniform Conditioning. And that opens up this new dialog box. And as you can see on the left-hand side, we've got a sort of workflow, input data, decluster, variogram, etc. And so you work through those in sequence, and each those processes is progressively setting up your data. The first part would be setting up the input data, which would be your samples, setting up your grade field, and defining the input model, and whether you have a domain field and any domain code within it. The next part is declustering. So whether you have already got decluttered weights in your input data, you can use the first option, or the second two options just enable you to decluster just using this dialog. Find the decluster grid and the decluster origin. That'll produce a new file. Then you just define your variogram, so there's much to add to that one. And then this is really the first part of the uniform conditioning analysis. We specify a series of SMUs. You can see where it says SMU block. You can append a number of different SMU sizes in there, and we will then analyze each of those SMUs and then create a global grade tonnage curve for each of those SMUs, which then compare against the panel size. Another part in the lower area of this dialog is the information effect. So the information effect, we can choose to ignore, or we can calculate. This runs a process which runs the change of support option, the new process which just runs in the background. But once this has been run, we can view the global grade tonnage curve, and that opens up the plots window, and we have a new scatter plot option to not only just do a scatter plot with points, but also now scatter plots with curves. So we can actually create the grade tonnage curves in the scatter plots window. And what we can see is the difference in grade tonnages at different SMU levels. So having looked at the different grade tonnage curves SMU, we can then create the panel block model. And we can either run this to calculate the creep values, which will actually estimate the creep values into the model, or if we've used an input file which has got creep estimates already in there, we can use those values model. Then we set up the number of SMUs per panel, and also define the number of cutoffs based on the grade distribution. And then we create our panel block model. And what this produces is similar to if we're running something like indicator kriging or potential Gaussian simulation. At each of the cutoffs, we get the probability above cutoff and the grade above cutoff and the grade below cutoff. So that tells you it's a non-linear process. We're looking at grade above cutoff. So the output of this is is actually a panel model, and we can see the grades that have been defined, in this case by ordinary kriging, and comparing them against the sort of dots which you can see, which are the samples that have been used. And you can see that the grade of the models to represent fairly closely the distribution of grade seen in the sample, although of course, because the panel size is pretty large, we don't see any granularity. So the final part of the uniform conditioning wizard is actually to carry out localized uniform conditioning. And this will essentially in the background create a plot model at the SMU size, and then it will calculate the local uniform condition grade into that plot model. It looks something like this in this particular case. So you can see there's far more granularity in the data if we compare that against the ordinary free test. So as well as the uniform conditioning wizard, which I should add, if you are running a macro, you run the uniform conditioning wizard, it will save all of the processes that have been run to that macro. But if you weren't keen to use the wizard and you wanted to use the process individually, this implementation has created new processes, Gauss and AM, provide Gaussian animal poses, subcore to model the change of support, the information effects, UNIFCOND, which carries out uniform conditioning on the panel model, and LUNICOND, which carries out localized uniform conditioning to produce the SMU model. So, in terms of further development, DataMine is certainly going to continue to incorporate new features into Studio, and we're currently assessing the next edition of functionality that we're going to work with Studio Variant to add to Studio. And it's likely in the future to include things such as co-creeping support, and parallelograms, and more robust multivariate analysis. But I'm just going to break into showing you the process in Studio 3. So under Models Uniform Conditioning Wizard, just brings up this uniform conditioning dialog, and it's a very simple dialog which auto-populates when you add your data. Just run through each of the processes to create your panel model, global grade tonnage curves, and localized uniform conditioning as well. And after having run one of the processes, for example, if we look at global grade tonnage curves, there's an option to view the global grade tonnage curves, and that would take you to the plots window. And slides. You can see that we've got a scatter plot line chart that has been created. So when you view them, it automatically creates these plots. So we've got the global grade tonnage curves, the SMU model summary, and model histograms based on the localized model. So that's all I was going to say for this presentation. I hope it's been useful and informative. Haven't delved too much into the technical detail of the process. Obviously, there's a lot more that can be said. But by all means, if you have any questions about the process, don't hesitate to give me a call or email me on jonathan.graham@dataminesoftware.com. But what I'll do now is I will just hand you over to Dinny, who will do a wrap-up. So I'm going to share my screen.
Great, thanks, Jono. So this marks the end of the webinar. Thank you all for attending. We hope you found the content presented valuable. You will soon be redirected to an online feedback form. It will take no more than a few minutes to complete. So if you have the chance, we would appreciate your feedback on how today's webinar went. We will also send out follow-up emails to all of our attendees. This email will provide you with a recording of the webinar as well as necessary details to contact Jono should you have any questions. We look forward to hearing from you soon, and thanks again for tuning in.
Okay, thanks very much. See you soon.